Ila Varma got her PhD in 2015 from Princeton University under the guidance of Manjul Bhargava and Richard Taylor, because, you know, one Fields medalist or one IS professor couldn't keep up with her. She needed both of them. She was a postdoc at Columbia, an NSF postdoc at Columbia and Harvard, and then she had a position for 1 year at UCSD, but they couldn't keep her, and she moved to Toronto. Don't know why, because, you know, San Diego's better. Her research is in number theory, but it spans wildly different areas of number theory. From one is arithmetic statistics on one side, and Galois representations, p-adic modular forms on the other side. And I know that might sound like maybe the same thing to a lot of people who are in number theory, but let me tell you, it's super rare to have somebody who works in these two things separately. I think the overlap is like 5 people total. And Ila's one of them, and she's made contributions to both of them. But maybe I should say that even before she did all of this, AWM spotted her potential in 2009 when she got an honorable mention for the Schaefer Prize. And then finally the world caught on, and in 2020 she got a Sloan. But somehow one of the things that is so nice about AWM and this setting is that we get to see somehow the whole person. And Ila is so much more than the sum of her research accomplishments. She's one of the most humble people that I know, despite being brilliant and adventurous. And she's so intentional about making every environment she's in, including mathematics, better for everybody and more welcoming. So basically, she is who I want to be when I grow up. And with that, arithmetic statistics.
All right. I was really excited to give a chalk talk, personally. This is my first in-person talk since March 2020 in Chicago, and I'm very excited to be here. There's so many people I've met over the last 2 years that I finally get to see in person, and it really warms my heart to know everyone's actual height in comparison to their Zoom screen height. So, all right. So I'm going to talk about a part of arithmetic statistics that I think a lot about, which is number field asymptotics. And I wanted to sort of maybe start where the problem started in my life, the first time I heard something related to this problem, and that was in a Galois theory class. And so I think of sort of the origins of this problem as related to the inverse Galois problem. Which just asks, does every finite group appear as some Galois group of some number field K? We can specify over Q. And so, because Alina just reminded me that we might have lots of non-number theorists in the audience, I'm gonna just remind us that a number field is sort of a vector space over Q that has sort of a field that satisfies field properties. And so usually any number field can be written as taking the polynomials over Q and modding out by some sort of f of x. And so one can ask, how do the roots of f of x permute? Okay? And so asking how the roots of f of x permutes is related to the question of what is the Galois group of k over q. So what are the different ways we can change around the roots? And so we think of the Galois group, usually denoted as Galois k over q, as sometimes people like to think of it as a group of symmetries. What I just said is you can think of it as acting on the roots. And for a number field, we always expect this to be finite. So this is a group, a finite group. And so this is an open problem. Does every finite group appear as the Galois group of a number field? This is still an open problem, but like for most people who have sort of thought about this problem, the idea is that the answer should be yes. And so as soon as you think the answer should be yes, why don't you take the problem further and make it a further open, further harder question? And so we can think of this as sort of the non-statistical version of the question that comes up a lot in arithmetic statistics. So to make it sort of more statistical, we can ask the question, how many number fields with Galois group G are there? So fix a G and just ask you can ask how many different f of x's are there with Galois group G, but there's one thing about number fields that's true, that there could be two different choices of polynomials giving you the same number field. So we really sort of want to make sure we don't think about it too much in terms of polynomials. We really want to think about it in terms of the number field. And sort of if you ask this question, I mean, first, if the inverse Galois problem is open, there's probably Galois groups G for which we don't know if there's even one, okay? But for the most part, since we believe the inverse Galois problem to be true, that there is at least one, it turns out that sort of if we ask this later question, if there is one, we expect there to be infinitely many usually. So as soon as we think there's one, we somehow think there's going to be infinitely many, and this is sort of where we come from the inverse Galois problem to a question in arithmetic statistics, because now we want to understand how that infinitely many grows, how large it is for different Galois groups, how do they compare, and things like that. So, so the answer, the first answer is infinitely many, if there is one. And by answer, maybe I should write something else. Hope? I don't know. Expectation. Expectation is probably the better word. And so now we want to ask how do they grow? What kind of infinity are we dealing with, basically? Okay? And so we're going to ask the question a little bit more precisely. So we're going to let d greater than 2 be an integer, right, which is going to be the degree of the number field. So number fields are secretly vector spaces over Q, and so the degree d is just the dimension, if you think of it as a vector space over Q, okay? And then the Galois groups on a degree d extension have the property that they always live inside the symmetric group of d letters, okay? And they have to be transitive, they have to sort of move all the roots possible. And so we fix a D, and we also fix a potential Galois group G, but we need it to sit inside the symmetric group with D letters. And so then we can ask about the set. So I'm gonna make a fancy F. dg is equal to k, all number fields with degree d, such that if we take the normal closure, k itself might not be Galois, but if we can take k to be Galois, that sort of makes the question a little bit easier, but we don't have to. And so we want the Galois group of the normal closure to be exactly the group that we chose. And then we can ask the question, we can obtain the quantity ndg of x is equal to the number, the size of number fields in this set we defined But I said the answer is that it's infinitely many, and so we have to have sort of a way of talking how this set grows over time. And so with number fields, we have a tendency to use what's called the discriminant. This discriminant you can think of as in terms of polynomials, but sort of if you want to stay on the number field side, you can think of it as sort of the volume of the lattice, telling you how big sort of an integral lattice is inside of your number field. Okay? So we say that the discriminant of k's absolute value has to be less than or equal to x. And so we can ask the question of how does, the precise version of the question I was asking earlier is how does n d sub g of x grow as x tends to infinity? And so sort of the first thing to do is maybe start with all the simplest things to fix. So you can take the case of d equals 2, which is quadratic fields. We're just looking at quadratic polynomials. Okay? And the discriminant in the quadratic polynomial case is sort of the same as the discriminant in the number field case. You can think of that as a good analogy. And then we can ask what are the transitive subgroups of S2? There's only one, it's S2 itself, so it's just the group of order 2. And so you could ask how many you could ask this question, how many quadratic fields are there up to a bounded discriminant? Okay? So simplest case is d equals 2 and g equals S2, but maybe people want to think about that as z mod 2z or c2, whatever sort of the notation is. Okay? And here we're in a case where there's no extra Galois groups. There's only one transitive subgroup. It's a little too small to have anything else. So we're really thinking about just how many quadratic fields are there of a bounded discriminant. And it turns out quadratic fields we can think of them as Q adjoin root D, where D is square free. And choose it to be an integer. And probably we're not going to choose D to be 0 or 1 though. Don't allow those. Okay? And so in case this is new, I just want to say that this is things of the form A plus root D, where A and B are rational numbers. You can see sort of the two-dimensionality of it. And we can multiply these things because we know how to multiply them in the real numbers or the complex numbers, and so that gives us a field definition. Okay? And you can also say that, well, for different d's, if you took, like, for example, d equals 2 and d equals 8, you would get the same field. Because anytime sort of d is off by a square, then it'll sort of be factored out, and you can use the fact that you have denominators and things like that in A and B to sort of get rid of those factors. Okay? So it turns out that quadratic fields are sort of in the set of quadratic fields, or maybe I'll write it as a new line, that this set we defined, F2 S2, okay, is in correspondence with the set of square-free integers that are not 0, 1. And I mean, you could think of it as the D that I wrote up here, or you could think of it as in terms of the discriminant. They're sort of, I mean, both of them are different ways to think about this correspondence, but they all come down to the same thing, where you really want to count how many square-free integers there are below x. Okay? And so the question of n2 S2 of x asks the question of how many square-free integers are there up to x? And then again, we're asking this question as x goes to infinity. So I don't mind that I can throw out 0 and 1. If I can throw out a couple, and as long as I'm trying to understand the asymptotic, then I have an idea of what's going on. And so in this case, it turns out the number of square free integers is, I can write the limit as x goes to infinity of this n to s2 of x is equal to 6 over pi squared x plus something like O over root x, right? And this is, you could sort of really think about the question analytically now. I mean, sort of, I was talking about a lot of algebra just now, and I just moved into analytics, and so of like trying to count, how would one count square free integers? And you could use sieving techniques. You could try to sieve out all the squares, you know, things like that. I think I don't want to go into too much how this asymptotic is proved, but I will point out that it has a relation to the Riemann zeta function. 6 over pi squared is a value for the zeta of s. And so sort of the analytic methods such as contour integration and such can be used to help you with this kind of question. Okay? So this is just sort of, this is maybe the grounding example, and sort of want to talk about the general question, hopefully if we feel a little bit comfortable now with this. So the idea in general, oops. So when I mean for general D and general G is that the limit as x goes to infinity of n dg of x should look something like a constant, which I'll call c dg, times x to some power, a dg. We're going to expect the maximal value of a dg to be 1 in general. So there's an expectation that if you just take number fields of a given degree, ordered by discriminant, that they should be at most growing like x, like a rational constant, or not some sort of constant times x. And so ADG will be, in general, smaller than 1. Sometimes, if you see it in the literature, people will write 1 over ADG instead of ADG to indicate that. And then we take the log. If it turns out that ADG is less than 1, then log factors can show up. So we get log x to the BDG. And so we can ask sort of the question of, are there general formulas for ADG, BDG, and CDG? Okay. And I'll say that maybe a lot of my research has to do with sort of general formulas for CDG, and what do they mean? What kind of interpretation can we get out of them? Okay. So just to summarize the previous case, we saw that CDG was 6 over pi squared. Sorry, let me write it with the 2's. C2, S2 is a 6 over pi squared. B2, S2 was 0, and A2, S2 was 1. And then we sort of expect that, that if A2, S2, or in general, if A dg is equal to 1, then B dg has to be 0. These are sort of expectations of the asymptotics. And so, and I think a lot of work had been done on sort of what A and B have to be, some of it incorrect, but still a lot of thought had been put into it, while as we really don't have an idea for what we expect for the constants C. And I find the constancy interesting because oftentimes, I didn't write it here, but here we have the 6 over pi squared in the example we did. I don't know why I'm doing that. Yeah, okay. And if you sort of know its relation to the Riemann zeta function, you can write 6 over pi squared as an Euler product if you wanted to. And so there's this idea that if you can write a constant in terms of an Euler product, is there an independence of sort of primes or a sort of local global principle? Why would we get in an analytic statement going for like a limit as x goes to infinity, sort of a really sort of nice algebraic quantity in front of the main term? What does that mean? And so that's really the question that I've been thinking about for a while. But it does, I mean, there's also sort of these questions about A and B. You really want to know the general growth. And even these things are a little bit unclear right now as to what the actual conjecture is. Okay. So I will try to talk in generality a little bit. Right? So there were a lot of results done, sort of the quadratic case that we discussed. It's like kind of unclear who to give credit to. Maybe it's always unclear who to give credit to when you go back. But I think in this case, it's like really, even amongst the big names, it's like hard to tell who you would attribute to. But it's sort of an older result, a classical result. And then sort of the next case you could think about doing is just like, let's go up degree 3. Let's go up to degree 3 and see what happens. And in those cases, that's work started in about the 1950s. So in Kohn, in 1954, thought about the cubic cyclic case. So when the degree is 3 and the Galois group isn't as big as it could be, we have sort of a cycle between the roots. So you have C3, C3, B3, C3, and A3, C3. I can tell you this is a half, this is 0, and this is a complicated thing, but I'll write it down still, just so we can see this Euler product notation. And then I think the other sort of big work that really, in terms of techniques, these two works in the degree 3 case, like, were very different. Okay? And so it's interesting that Davenport-Heilbronn's paper was done in 1971. One of them was dead by this time, and also Kohn in 1954 already knew of this result. When you can see in their paper, they write about the Davenport-Heilbronn result. And this is the other case. Again, if we think about the symmetric group on 3 letters, there are 2 transitive subgroups. There's the cyclic group of order 3 and the full subgroup itself. So Kohn did the first part, and Davenport-Heilbronn did the second part of C3S3 being now a zeta value, 1 over 3 times zeta of 3. B3S3 being 0, and A3S3 being 1. And so if you've never thought about asymptotics like these, I want to point out that what I'm saying here is that the number of cyclic cubic fields ordered by discriminant grows as x to the 1/2. Okay? And then here we're saying that the number of cubic fields with Galois group S3 grows as x. So I want to just point out that what that means is that 100% of cubic fields are S3. And so I said it that way specifically because we're taking percentages over an infinite family, and so we can have, for a lot of them, for an infinitely many one, as long as they are sparse, we can have them be negligible. And so the idea is that if you pick a random cubic field, if you have some ability to pick a random cubic field, you will always get a Galois group that is S3. Now the interesting thing is that if a human picks a random field, we know that that's not so random. It has like higher likelihood to be a cyclic field, because those are the ones I think we like a lot. But I'll just say that there's sort of really 2 different techniques that come up in these 2 papers. For cone, they use sort of these analytic methods related to what I was talking about in the quadratic fields case, but they also use sort of class field theory, which was coming up a lot in the 20th century. Okay? And so sort of they use the fact that we know a lot about extensions of Q when they're abelian. Turns out we know a lot about them, and especially when they're cyclic. And so class field theory really tells us exactly what should happen in those cases. If you are in the know, basically you can ask yourself, where do cubic cyclic fields, which cyclotomic extensions do cubic cyclic fields live in? And that's how sort of this, if you answer that question and sort of enumerate it, that's where all this information came from. Okay? And for Davenport and Heilbronn, there were sort of very different techniques were used, in particular, what's usually referred to as geometry of numbers, or GON. I guess this is class field theory. And sort of geometry of numbers goes back to the idea of, usually attributed to Minkowski, that if you have a lattice and you draw some shapes inside there, how many lattice points can you pick up is related to the volume of sort of the shape that you're drawing. Okay? And so I'll just say that, well, I guess I can talk about the quartic case. Well, I guess I'll talk about the cases that we know, sort of the general answers. Okay. So a lot of work was done, Cohn, Davenport, Heilbronn, and a lot of work was done after that point. But I sort of want to talk about the results where people were dealing with D and G in a general fashion. We weren't working with these specific cases of D and G. And so the first case was Wright and Maki. Who worked separately, so I guess I won't put a dash in between them. Wright and Maki, who sort of dealt with the case of G abelian. Okay. And so they dealt with the case of thinking of ADG. They found out that there's a formula for ADG of 1 over D times 1 minus 1 over P, and BDG is some number n sub P over P minus 1 minus 1. Okay. And P here is the smallest prime dividing the size of G. And n sub P here is the number of elements of G of order P. And Wright and Maki built on sort of the methods of Cohn, built on these class field theory methods. Again, class field theory comes quite in handy when you're looking at abelian extensions. Okay? Since I'm looking at time, let me think for a second. I guess I'll just say that Mala, and I'm also going to write Turkelly's name down. And I'll say, for G abelian, they predict, let me make sure, or they prove, Wright and Maki, that ADG and BDG have to follow these formulas. And Mala, and then later Turkelly, thought about the non-abelian case, sort of thought about what Wright and Maki did, wasn't able to sort of prove what's going on, but made predictions. And so they made predictions in the G non-abelian case. Mala first made the predictions in the non-abelian case, and there were some mistakes. Some counterexamples were proven. And Turkelly sort of did analogs of these questions in the function field examples, more geometric examples, and created a fix. Okay? So they predict, and just because of time, I'm not going to write down what they predict because the formula is a little larger. So I'll just say they predict ADG and BDG. And so I just want to end with saying sort of, what about CDG? The constant in front of the main term. And sort of these predictions haven't been done. In some sense, it's really unclear, even when someone writes down a prediction. Sort of a secondary question that comes out of it is like, okay, I have this prediction, and then maybe the conjecture is when is that prediction right, is like maybe the way to think about it. So Bhargava made predictions. I mean, Bhargava proved CDG for a variety of cases, but also made predictions for CDG in the case where G is equal to SD. So the biggest case, when you're in the degree D, and your Galois group can be as big as possible. Wrote down really beautiful formulas. Right? Usually sort of akin to sort of what we saw in the Davenport-Heilbronn case, the zeta 3 as the CDG. And so a lot of my work now sort of thinks about the case when G is not equal to G is not equal to SD. And so my work, I've done the case of D equals 4. I've thought about G equals D4, the symmetries of a square. And in that case, it turns out that if you apply sort of Bhargava's predictions, even though they're not for a smaller group than S4 or SD, if you apply those, so you sort of realize that the predictions don't work. So in the D equals 4 case and the G equals D4 case, the constants C for D4 does not satisfy the analogous prediction. And so there's a lot of questions as to why that might be the case. And sort of that's, I mean, I'll stop there. But I'll just say that that's sort of where a lot of maybe, I haven't like told you a particular result or anything like that, but a lot of my results are sort of around this question of what's going on with these constants. And even in specifically the quartic case, the D equals 4 case, what's going on with these constants and how can we predict them? So I'll stop there. Thank you.
Okay, we have time for a couple of questions and then you're free to go to lunch.
So this is like a very naive question, but like in the C4, D4 case, is the prediction too high or too low, or is that not, you can't really attach
I should know
adjectives?
that, shouldn't I? I should know if it's too large or too small. The way I would say it is that I was talking about these Euler products and the expectation, and at least maybe the hope, maybe not the expectation, but this is a hope, that the constants would be Euler products. And it seems like in the D4 case that it's and this is why I don't know the answer to your question, either a sum or a difference of two Euler products. And so I don't know if it's bigger or smaller, but I hope that gives you a little bit of context for what's going wrong. And so there's this mysterious second Euler product showing up, and sort of you can think of the question of what's going on as what is that second Euler product? Where does it come from, and why does it disappear in sort of the big cases like SD, but in sort of smaller groups it can show up?
Well, then let's thank Ila again. And